All right, so now we'll look at the tangent line problem. Um, well, we're going to try to get an approximation for the slope of a line tangent to a curve at a certain point. And a tangent line is just a line that passes through the graph of a function in at least one place of interest, called the point of tangency. And what we're going to do is we're going to start off with a secant line. So here's our function, f of x equals x squared. And what we want to do is we want to start off with a line secant to f of x equals x squared, such as this. You see it's a secant line because it passes through the graph at 1, 1, because 1 squared is 1 is on the function. And it also passes through the graph at 3, 9. So 1, 1 and 3, 9 are 2 points that are shared by both the blue secant line and the function f, x squared. So what we want to do is we want to find the slope of this secant line. Well, the slope of the secant line is going to be y2, 9, minus y1, 1, over x2, which is 3, minus x1, which is 1. This turns out to be 8 over 2, which is 4. All right, so we have here that this blue tangent line, or sorry, secant line, this blue secant line, the slope of that secant line is 4. 4. All right, now here's what we're going to do. We're going to bring this point closer to this point 1, 1. The point 1, 1 is where I want to calculate the slope of the tangent. So what I'm going to do is I'm going to keep 1, 1 fixed, and I'm going to have this point get closer and closer and closer to 1, 1, coming along this function x squared. So the next point is closer. So I still have the point 1, 1, and now I have a point closer to 1, 1. The x value 2 is closer to this x value 1 than the original x value of 3 was up here, right? So this point is getting closer to the point of tangency 1, 1. Let's calculate the slope of this secant line. Slope of this secant line is going to be 4 minus 1 over 2 minus 1, or y2 minus y1 over x2 minus x1, which is going to give me 3 over 1, or 3. So the slope of this secant line is equal to 3. All right, let's get even closer to 1, 1. Let's make this point move even closer to 1, 1. So here's another point. This is 1.5, comma, 2.25. All right, so I want to find the slope of this secant line. It's going to be y2, which is 2.25, 2.25, minus y1, which is 1, over x2, which is 1.5, minus x1, which is 1. So this gives me, let's see, we'll have 2.25 minus 1 is 1.25, and 1.5 minus 1 is 0.5. And when I do this division, I get 2.5. So see, my tangent line slopes are changing, or my secant line, sorry, my secant line slopes are changing. The first slope was 4. That point is further from 1, 1 than any of the others. The next tangent line, the next secant line has a slope of 3. So this secant line has a slope of 3. That point is closer than the original. Now I get this secant line has a slope of 2.5. Let's calculate another one. So this one is even closer. This one is only, the difference between this x value and this x value is only 0.1. So it's even closer. Let's calculate the slope of this secant line. So the slope of the secant line here is going to be, we have 1.21 minus 1, y2 minus y1, over 1.1 minus 1, x2 minus x1, which gives us 0.21 over 0.1, which is exactly 2.1. So that's the slope of this secant line. Notice these 2 points are extremely close together now. Let's get even closer. So here's the slope of the secant line. If we get even closer here, we see that we have this point is within 1/100th of the number 1. The last point was only within 1/10 of the number 1, and this one is in within a half, 0.5 of the number 1. So we're getting closer and closer to 1 on the x-axis. This is as close as we've been so far. Let's calculate this um, slope, the slope of this secant line. All right, so we'll have 1.0201 minus 1 divided by 1.01 minus 1, which gives me 0.0201 divided by 0.01. So I get 0.0201 divided by 0.01, which is 2.01. All right, so let's recap here. We had a bunch of secant lines. The first secant line that I had gave me a slope of 4. The second secant line I had gave me a slope of 3. The third one gave me a slope of 2.5. The fourth secant line gave me a slope of 2.1. And the last one I just did gave me the slope of 2.01. So each successive secant line gives me a slope closer and closer to the number 2. Do you see that? If you continue this on forever, you would get arbitrarily close to the number 2. So an estimate for the slope of the tangent line. An estimate for the slope of a tangent line would be the slope of the tangent line I would expect it to be approximately 2. I would expect it to be approximately 2. Let's actually try to find that using a limit, okay? So let's go through that whole process, except in this case, let's do it instead of having actual numbers. We'll only look at the point of tangency 1, 1, and then we'll look at another arbitrary point. Let's call this arbitrary point up here x, y. But we know that the y value for this function is actually x squared. So there I have the black point, which is my point of tangency. That's where I want to calculate the slope of the tangent line. And I have this blue point up here, which I'm going to allow to get closer and closer and closer to the black point. So here we go. So what I want to do is I want to find the slope of the secant line. I'm going to call it msec. The slope of the secant line, as far as these 2 points are concerned, the blue point and the black point, is going to be y2, which is x squared, minus y1, which is 1, divided by x2, which is actually x, minus x1, which is also 1. So here is the slope of my secant line. This would be the slope of my secant line. What I want to do is, in order to find the slope of the tangent line, I'm going to call that slope and put the subscript tan. This represents the slope of the tangent line. I want the slope of my tangent line, and it's going to be the limit as x. This is x, right? I want that x value to get closer and closer to the number 1. So this is the limit as x approaches 1 of x squared minus 1 divided by x minus 1. X squared minus 1 over x minus 1. All right, so let's try to calculate this limit. This limit, as this point gets arbitrarily close to the black point, this limit will give me the slope of the tangent line, the slope of the tangent line. So upon initially plugging in 1 for x, I get 0 over 0. In the case where we have two polynomials, what I want to do here to calculate the limit is I actually want to factor this so that I can find a function that agrees with x squared minus 1 over x minus 1 at all but one place. So I have x minus 1 on top times x plus 1. I can factor the numerator because the numerator is a difference of squares. and the denominator is x minus 1. So you see, the factor x minus 1, which made the numerator and denominator both 0, now can cancel out. And I see that the slope of the tangent line is just the limit as x approaches 1 of x plus 1. Well, that's good, because this limit I can actually calculate just by plugging 1 in. So this is actually equal to 2. So you see, the slope of the tangent line is equal to 2, which is exactly what I approximated it to be with this process right here. So that process is a limiting process, so I introduced the limit, and I calculated the exact slope of the tangent line at the point where x and y are both 1, because x is 1 and y is x squared. So this is how we can find the slope of a um, tangent line to a point, or sorry, slope of a tangent line to a function at any at a given point, this point of tangency.